Hello everyone. So this is the 12th week of interaction session for the NPTEL course on control systems. So this is the last uh, session that we'll have for taking a number of problems. There would be one more session which would be held next Monday, but I'll talk about that later. But yeah, this is the 12th week and this is the last week where we are going to deal with the theoretical concepts on compensators. So the class will deal with questions mostly related to lead compensator, lag compensator and lead lag compensator. And yesterday when we were doing the 11th week, then we saw a number of questions on Nyquist stability criterion. So before that, we understood how do we make Nyquist plots, and then we came to the uh, then we understood the mapping theorem and how this Nyquist stability criterion is used to define the stability of the system. So the number of encirclements that you have around minus 1 comma 0 point in the GSHS plane, that should be equal to negative of the number of poles. Like it should encircle p number of times in counterclockwise direction. If that is not the case, that means the system is not stable, right? So we have already seen this. Right. And then uh, we saw a few questions on relative stability, because before this we were always defining absolute stability. That means where are the poles actually present. So if they are present in the right half of the S plane or left half of the S plane, and then we said that the system is stable or unstable. But how do we compare in between two systems? That means if there is a system which has poles lying, let's say, somewhere over here, and there is another system which has poles lying somewhere over here, which of them is more stable? More stable means which system is likely to become unstable at very later point of time, at infinite time. So if we talk about this system, it is very closer to the imaginary axis, and the exponential decay for this system with these poles would be at a faster rate, at a slower rate, whereas with these poles the decay would be at a faster rate, because let's say if it is 9, if it is 1, it would be e to the power minus t, and it would decay at e to the power minus 90. So this is more robust to any parametric uncertainties, unmodeled dynamics, or any kind of noise in the system, whereas this system would not be able to uh, help in dying out of all those uncertainties quickly. So this is likely to become unstable with change in the when uncertainties are introduced to the system, whereas this is less susceptible to the disturbances, right? So we say that this system is relatively less stable as compared to this system. So there comes the concept of relative stability, where we say that how far we are from reaching the verge of instability in terms of magnitude, in terms of phase, both of the ways we define. If we say in terms of magnitude, it is how much magnitude are we away from minus 1 comma 0 point, how much gain are we away from reaching minus 1 comma 0 point that would make the system unstable. And then if it is about the angle, what amount of phase uh, addition would actually cause the instability in the system, right? So both of these conditions, so we saw that there are various performance parameters, performance specifications. uh, we saw gain, crossover frequency, phase crossover frequency. Then we saw gain margin, phase margin, then we saw bandwidth, then what did we see? Cutoff frequency, cutoff rate, and what did we see? Resonance frequency. So all of these are the performance specifications in frequency domain. What about time domain? We have rise time, peak time, maximum peak overshoot, settling time, right? So these are the performance specifications in time domain. Both of them are different ways of analysis, but eventually there are some relations. For example, uh, phase margin is, if we, it is not direct formula, but it is just empirical formula in which phase margin is approximately equal to, I don't remember this factor, it is uh, I believe it is 100 times zeta. So this is not the direct relation, this does not come from formula, but it is approximation of the formula. But this works only when zeta is less than 0.7, then this holds true. So there are relations in between both of these parameters, frequency domain and time domain, and we saw all the performance specifications. We did a couple of questions where we tried to find out what is the gain crossover frequency, phase crossover, gain margin, phase margin, all of that we did yesterday, right? In case you have missed, the lecture is already available on YouTube. Okay, so after this, let's move to lead compensator. Why do we need compensators in the first place? So I think I should have added one more slide here, but I haven't added. Okay, then we'll see here. We need compensators because, or to improve system performance by uh, simultaneously achieving stability and accuracy. All right, so this is the reason. The main thing is stability and accuracy. We want to have more of noise attenuation. At the same time, we want the system to be stable. It should not become unstable. We want to have less steady state error, right? So for all of these reasons, we need compensators. Okay, and then there are two types of compensators: lead compensators and lag compensators. You can relate both of them to either PI or PD controller. So if it is a lead compensator, it's similar to a PD controller. If it is a lag compensator, it is similar to PI controller. Okay, so Let's start from here. So consider unity negative feedback system where HS is 1 definitely. Okay. So what does lead compensator do? It adds sufficient phase lead to reduce any excessive phase lag associated with the system. So this phase lag is the cause of reaching instability. At some point of time, this phase lag becomes minus 180 degree and then we reach the verge of instability. From where this minus 180 degree comes? 1 plus GSHS is equal to 0 is the characteristic equation. GSHS is equal to minus 1 is called reaching the verge of instability. The magnitude is 1 and the phase is minus 180 degree. So if any lag is associated with the system, which is minus 180 degree in this case, then the system becomes unstable. So we want to add a phase lead so that the system does not have excessive phase lag, and then we are able to like stabilize the system. So this is the reason. So the way lead compensator is defined is the following. So lead compensator has two components. One is alpha. In case you want to replace alpha by gamma, what you can do, instead of having s plus 1 upon alpha t, you can write s upon s plus gamma upon t. This is another way. It is just to, so if you like to have alpha in between 0 and 1, that's okay. If you want to have gamma greater than 1, this is the way of doing it. Okay, and t is always greater than 0 because it is time constant. So from here, the compensated transfer function is given by the following equation, which basically has 1 0 and 1 pole, right? The 0 is minus 1 by t and pole is minus 1 by alpha t. Now based on the sign of alpha, you can say which of them lies where, like relatively 1 by t should lie where, and minus 1 by t should lie where, and minus 1 upon alpha t should lie where, to the left or to the right of 1 by t. So that can be found out from here. So this is the example, this is the way how lead compensator is defined. If we talk about lag compensator, you'll get a term beta over here, and this beta would be greater than 1. So we'll see that, but for now this is a lead compensator. And what does it do? So it has an open loop 0 at minus 1 by t and an open loop pole at minus 1 upon alpha t, right? Okay, I'm not going into all the derivations that were covered, but one thing is, when you want to design a lead compensator and you draw the Nyquist plot, you'll find this to be holding true. The Nyquist plot would be a semicircle of this radius that is centered at this point. All right. So, and what is Nyquist plot? Nyquist plot is so when you are varying omega, how does the transfer function, imaginary, and so the plane consists of real part and imaginary part, and how are the real and imaginary part located as omega varies from 0 to infinity. All right. So phi m is the maximum phase lead provided by the lead compensator. That is what we want to do, and it is provided at some omega m frequency. That omega m, so from here you can find out tan phi m, and after this we want to find out omega m. For finding out omega m, this is the equation that we use. It comes from proper derivation. I'm not going into derivation, but the thing which is important is omega m is a geometric mean of both the poles and zeros. Okay, so what happens when we use lead compensator? Why do we actually use it? So we observe from so this is one of the log magnitude plots of an example taken. So what do you see here? Do you see the graph somewhat similar to PD controller? So if you remember, when you draw the Bode plot of PD controller, it appears to be like this, where this is the corner frequency. It's of the same nature, right? So what happens here? You have a 0 and you have a pole, and therefore you have two corner frequencies. So this is the graph that you get for it. If you try it with some example which is also given here, you can get this. So from this log magnitude plot, what do we infer? So we do infer that the magnitude of the open loop transfer function at low frequency is decreased, potentially leads to increase in steady state error. Right? Now, let's say if I talk about steady state error, what it is? 1 upon 1 plus kp, or 1 upon kv, or 1 upon ka. Right? These are the steady state errors for type 1, type 2 and type 3 systems when uh, step input, step impulse, step, and ramp and parabolic input, not impulse. Step, what I said after this? Step, ramp and parabolic input. So when all of these are provided, this is the steady state error. So from here, you can see that since this value is really low, the in the beginning, at lower frequency, the value of the gain is really low, right? Which means it leads to an increase in steady state error. If this gain is low, steady state error would be high. Right? This is what we overcome in lag compensator, but in lead compensator, this is the problem, that your steady state error would be high. Apart from this, if we increase Kc to address 1, if we increase the value of gain so that steady state error becomes less, then what would happen? Note the high frequency components would be amplified. So what would happen? If you, let's say, increase the value of Kc, your graph would shift here. Now these are the high frequency components, they would be even amplified. And what are these high frequency components usually? They are noise. So this is again a problem. So what happens? When you use lead compensator, the steady state error increases. If you want to address it, then your high frequency components would be amplified, and both of them are not good for the system. But what is the benefit of having this? Why do we even go for lead compensator? I think I haven't included it here, but the benefit of doing this is you can increase the bandwidth of the system. Okay, so a cutoff frequency would come at a much later point of time, where you'll be 3 dB below the steady state value. So this is one of the benefits. I would not go into example right now. Then let's move to lag compensator. So what lag compensator usually do? It is used to attenuate high frequency components of the system response. So before seeing why this is written, let's see this. So it is also defined in the same way. You can see it has 1 0 and 1 pole, but alpha lied in between 0 and 1, beta is always greater than 1. And again, these are the open loop poles and zeros. It has two corner frequency at 1 by t and 1 by beta t, right? Then you'll observe, if you plot the Nyquist plot, you'll observe that it is also a circle for omega varying in between 0 to infinity. It acts as a low pass filter while, so this is the basic graph magnitude plot for lag compensator if you try with an example. So you can see here, initially the gain is really high. If the gain is high, that means steady state error is low. So this is the benefit. Second thing, for higher frequency, the value of the magnitude is really less, means these higher frequency components are attenuated. So that is what is written here, that it is used to attenuate higher frequency components of the system response. It acts as a low pass filter because it allows the low frequency region to pass through but does not allow the high frequency region to move through. It has a low frequency gain. So it has low steady state error. It has higher frequency gain, and then it has, sorry, the low frequency gain, which is at this point, is really high. So this leads to lower steady state error, and gain crossover frequency for the compensator leads to reduced bandwidth, because gain crossover frequency would come soon as it is crossing this, and that would lead to reduced bandwidth of the system, right? So this is, so there are some advantages and some disadvantages in both of lead and lag compensators, right? So to overcome them, we go with lag lead compensation. Okay. So lead compensator, the benefit of using the lead compensator was it improves the stability margins, but may decrease the steady state error accuracy, right? And for lag compensator, it attenuated the high frequency components, but it decreased the bandwidth. What if we have combination of both of these? So the transfer function for a lag lead compensator is given by this, where this is the lead part and this is the lag part. Then it has 4 corner frequencies, 2 for lead and 2 for lag, and this is just multiplying both of them. So I think we don't have the plot here. Okay, in one of the questions we'll cover the plot for lead lag compensator as well. So the whole point is it improves transient response, enhances stability because it introduces phase lead at higher frequency, right? And for lag compensators, it improves steady state accuracy and it boosts stability at low frequencies. Right. But if we have a combination of both of them, then it would be helpful. Okay. Now, let's move to the first question. So, which one of the following statements is typically true about a lead compensator? It attenuates high frequency signals and worsens the transient response. No, it does not do it. It does not attenuate the high frequency signal, because we saw that the magnitude is even larger at higher frequency. And it worsens the transient response. No, it does not, because the bandwidth increases eventually. Second option is it improves the transient response. Yes, because bandwidth is increased. And it amplifies high frequency signal. Yes, it does. It is amplifying here. So this is the correct option. The third option is it worsens the transient response and amplifies high frequency signals. No. It improves the transient response and attenuates high frequency signal. No. High frequency signal is not at all attenuated over here. Alright. Okay. Let's move to this question. So a lead compensator introduces an open loop 0 at -2 and an open loop pole at -5. Then the corner frequencies are what? So just a second. Okay, so our transfer function is s plus 2 upon s plus 5 because it has a 0 at minus 2 and pole at minus 5. Then the corner frequencies. So this has to be represented as t1 s plus 1, t2 s plus 2, and the corner frequencies are 1 upon t1 and 1 upon t2. Corner frequency 1 upon t1, 1 upon t2, which is 1 upon 1 by 2 and 1 upon 1 by 5. So it is 2 and 5, right? So the correct option is D. I hope this is clear. Let's move to the third question. In same problem, the maximum phase lead in degrees provided by the lead compensator is what? Okay. So we did very similar question when we were doing Nyquist plot, and so the transfer function is s plus 2 upon s plus 5. We have to basically construct a Nyquist plot, find what is the maximum phase, and then at that point we are going to find what is the angle that is being provided. So basically finding the value of phi m. So it can be written as j omega plus 2 upon j omega plus 5 into j omega minus 5 upon j omega minus 5. From here what do you get? 10 plus omega square plus 3j omega upon omega square plus 25. Right. So once we have this, then what are we going to do? We have real part which is given by 10 plus omega square upon omega square plus 25, and imaginary part which is given by 3 omega upon omega square plus 25. Now construct the table. So this is the real part, this is the imaginary part, this is at omega equal to 0 and omega equal to infinity. So at omega equal to 0, the real part is,
Hello, ma'am. One doubt, ma'am.
sorry,
You are multiplying with the conjugate, you know, ma'am.
I'm not able to hear you clearly.
Uh, you have multiplied by the conjugate, you know,
Yeah, I multiplied by the conjugate.
but you multiplied with the j omega minus 5. Is it okay?
Oh, okay, 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 I understood.
Thank you, ma'am.
Actually we'll get this answer only because if I have done mistake here, I have also done mistake here, so eventually minus sign would come out, but no, writing this is not correct. Should be 5 minus j omega and 5 minus j omega, and you'll get this only. Even when it was a mistake, it was just that minus sign was cancelling out and things remained. Okay, so it would be 10 upon 25 here, which is zero point 0.4. And for imaginary part, when you substitute the value of omega to be 0, it becomes 0. At omega is equal to infinity, how do we get it? It becomes infinity by infinity form, right? So what will you do? Divide by omega square. So this would become 10 upon omega square plus 1 upon omega square, which would be 1, 25 upon omega square, right? As omega tends to infinity, this value would be 1, and for this it would be 0. Okay, because again if you divide, it would be 3 upon omega, and it would be 25 upon omega square plus 1. As omega tends to infinity, this also becomes 0 and this becomes 0. So it's 0 by 1, which is 0. So this is for omega is equal to 0 and omega is equal to infinity. We can also find that this is actually a semicircle. So if you find at 2, 3 more values in between 0 and infinity, you'll find it to be a semicircle, and it would look like the following. So what would be the radius? At omega is equal to 0, the real part is 0 0.4, and the at omega equal to infinity it is 1, and in both the cases the imaginary part is 0. So definitely it's going to be a semicircle like this. Now what would be the radius? It would be 1 minus 0 0.4, which is 0.6 by 2, which is 0.3. So the radius is 1 minus 0 0.4 by 2, which is 0.3. So 0.3 is the radius of the circle. Okay. Now, after this, our question is asking what is the maximum phase lead provided by the lead compensator. So maximum phase lead means if we draw multiple lines from here, this, 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 where, sorry, I made a mistake. If we draw multiple lines, where are we going to get maximum phase lead? It would be here. Right, all of these won't give you maximum phase lead. You'll get the maximum phase lead at the tangent of the circle. Okay, so we'll get them to be here. Now when this is a tangent to the circle, this line joining the tangent touching the circle and the center of the circle makes, both of the lines make an angle of 90 degree with each other, and this is the phi m, which we are supposed to find. This is 0.3 because this is the radius of the circle. This is 0.4 plus 0.3, and this is 0.7, right? So this point is 0.7 comma 0, right? So if we want to find out what is the maximum phase lead that is being provided, it would be sine phi m is equal to 0.3 upon 0.7. Okay, so from here you can find, if you calculate it, you'll find tan phi m to be equal to 0.474, and if this is the tan phi m, from here you'll get phi m, which would be approximately equal to 25.4 degrees. So this is your answer. Any confusion in this question?
No, ma'am.
Okay. So once we have found out this phi m, it happens at some frequency, and that frequency is called corresponding frequency, right? So how do we calculate this frequency? So we saw that tan phi m was equal to 0.474. From here, from the last question, tan phi m is equal to 3 omega upon 10 plus omega square, right? Because it will eventually lead to cancelling out of the denominator. So this is 3 omega upon 10 plus omega square. From here, if you calculate the value of omega, you'll get it to be equal to 3.16 radian per second. Okay, but since we are solving it as a compensator problem, we also saw that this omega is a geometric mean of 1 upon t and 1 upon alpha t. So it has to be 1 upon root alpha t. Okay, and then from here, what is the value of alpha and t? T is 1, right? From here, if we compare it to original lead compensator equation, what it should be? S plus 1 by t upon S plus 1 upon alpha t. This is the equation. So 1 by t is equal to 2 and 1 upon alpha t is equal to 5. So from here, t is equal to half and 1 by t is basically 2 is equal to 5. 2 upon alpha is equal to 5. From here, alpha is equal to 2 upon 5, which is 0.4. Right. So t is half and alpha is 0.4. So if you calculate this value, you will also get it to be equal to 3.16 radian per second. Okay. So both of these ways in which we are using the concept of compensator, or we are going with the whole approach of constructing the Nyquist plot and then trying to find out at what frequency we are going to get maximum phase lead. All right. Okay. Let's move to the next question. So in the same problem, it is desired that the low frequency magnitude in dB of the compensator sinusoidal transfer function be 20 dB. Then the parameter Kc is what? Okay. So our transfer function was Kc into S plus 2 into S plus 5. This is basically the gain for which we want to find out the value. It can be written as 2 upon 5 Kc into 1 by 2 S plus 1 and 1 by 5 S plus 1. Okay. Now we want to find the value of Kc at low frequency. That means magnitude value as omega tends to 0 would be what? 20 log. If you put the value of omega to be 0 in this equation, what will happen? All the terms would become, this complete term would become 1, and what would remain? 2 by 5 Kc. Okay. 2 by 5 Kc is the value here. It is in dB. It should be equal to 20 dB. 20 cancels out. Now, for getting, so what happens? Log 2 by 5 Kc should be equal to 1 now. When would it become 1? When? So this is at base 10, right? So 2 by 5 Kc should be 10. So from here Kc is equal to 25. So D is the correct answer. Okay, I hope this is clear. We'll move to the next question. So problem 6 to 11 are covered by this transfer function, whose planned transfer function is 1 upon s into s plus 3. It is desired that a lead compensator is used to design a unity negative feedback closed loop system with this plant. So if the lead compensator needs to provide a maximum phase lead of 40 degree, then the value of alpha is around what? So our GS is 1 upon S into S plus 3, right? So since we want 40 degree, sine of 40 degree is 1 minus alpha upon 1 plus alpha. This is we already saw. And from here, if you calculate the value of sine 40, it would be 0.642. So from here, you'll get 1 minus alpha equal to 0.642 plus 0.642 alpha. From here, alpha would turn out to be 0.217. You can approximate it to 0.2. So this is the correct answer. Okay. Once we have the value of alpha with us, then here we want to find out what is the value of omega m. And omega m should be 10, right? So from here, omega m is geometric mean, right? So 1 upon under root alpha t is equal to 10. So from here, t is equal to 1 upon 10 root alpha. 1 upon 10 root 0.22. Can anyone calculate this and tell me what it is?
Zero point two one three.
0.
0.213.
0.213, is it what you said?
Yes, ma'am.
Okay, so the correct option is B, 0.5. Okay, this is clear. Let's move to the next question. It is desired that the static velocity error constant be 10 per second, then the value of Kc, the gain, is around what? So what is Kv? It is limit s tends to 0, s, gs, hs, cs. Right. Now, from here, so this gs is planned transfer function. If you want to write as ps, it is okay. Ps into cs comprises of gs and hs is hs only. So from here you can write limit s tends to 0, s into Kc. What is the transfer function? S up plus 1 upon t upon s plus 1 upon alpha t. Right. Now, after this, the plant transfer function is 1 upon s into s plus 3, and this has to be equal to 10. So from here, ss cancels out, and as s tends to 0, what do we get? We get kc upon alpha, kc upon kc alpha upon 3, it is equal to 10. We know alpha values already, right? So kc is equal to 30 upon 0.22, which is approximately equal to 138.24. So in option, do we have? Yeah, we have 138. Okay. So when you wanted to have a static velocity error value, then we want to find out what should be the gain. So you just have to uh, write it in terms of the formula that we have for static velocity error, and then after that you just have to substitute s is equal to 0 and substitute the value of alpha that we found earlier, and from here you get the value of gain. Okay. After this, we have the lead compensator introduces an open loop 0 at around what? So open loop 0 is at minus 1 upon t, right? Which is minus 1 upon t is 0.215, which we already calculated. We'll get this to be equal to nearly 4.65. So this is the correct answer. The 0 of the system was minus 1 by t, and the pole of the system was minus 1 upon alpha t. So just substitute the value and you get the answer here. Okay. This lead compensator introduces at an open loop pole around where? Open loop pole is at minus 1 upon alpha t, which is minus 1 upon 0.217 into 0.215, the values of alpha and t, and if you solve this, you get it to be around minus 21.4. Okay, so it is minus 21.4. Consider the transfer function of the lead compensator whose parameters have been determined in problem 6 to 10. The low frequency magnitude of this compensator's frequency response transfer function would tend to around what? Okay, so low frequency magnitude of kc into s plus 1 upon t upon s plus 1 upon alpha t is 20 log kc alpha, right? Because as soon as you put the value of s to be 0, you'll get it to be kc alpha. From here you can put 20 log kc ka value is 138 and alpha ka value is 0.22. Can you tell me what is the value that we are getting in dB? All of these are very simple questions.
29.65, ma'am.
Okay, right. So if you find the nearest answer, it would be 29.5. So it's 29.5D. So it's just that we had to take the compensated transfer function. Are you saying something? Okay. So we had to just write down the transfer function, and then we had to transfer function of the compensator, and then we had to substitute s tends to 0 so that we get the value. Okay. After this, let's move to the next question. So which one of the following statements is true about a lag compensator? It magnifies high frequency components. It does not, right? It attenuates. It does not magnify. It decreases the low frequency gain. No, it does not. We have a very high frequency gain, so it does not decrease. As we have high frequency gain, the steady state error is decreased. It acts like a low pass filter. This is correct, because the plot of lag compensator looks like this. So so for these values of frequency, it allows it to pass through, whereas for the higher frequency region, it attenuates. This is the correct answer. Okay. Let's move to the next question. A lag compensator introduces an open loop pole at minus 20 and an open loop 0, sorry, a lag compensator introduces an open loop 0 at minus 20 and open loop pole at minus 2. Then what are the corner frequencies? So in this case, your transfer function for the compensator would be s plus 20 upon s plus 2, right? We have to find out the corner frequencies. It would be one upon T1 and 1 upon T2, right? So it would be 1 upon 1 by 20 and 1 upon 1 by 2. So eventually it would be 20 and 2. So this is the correct answer. Okay. Let's move to the next question. Consider a lag lead compensator where T2 is greater than T1. This is very important. Then which of the following statements is true? So we have to comment on lower frequency, lower corner frequency of the lag component, and okay, so it's all about both lower and higher corner frequency of the lag and lead component. That is what we want to compare. So let's find out what are the corner frequencies. Corner frequencies for lead and lag. Okay. For this it is 1 upon T1 and gamma upon T1, where gamma is greater than 1. For this it is 1 upon beta T2 and 1 upon T2, where beta is also greater than 1. So in both of these cases, if let's say I want to, let's check the first statement. Okay, the lower frequency of the lag component, let's find out which is lower and which is higher, because that would create even more problem. So in this case, this is lower, and since gamma is greater than 1, this is higher. In this case, beta is greater than 1, that means this is higher and this is lower, right? Now the lower corner frequency of the lag component which is 1 upon beta T2, would be greater than the lower corner frequency of the lead component, which is 1 upon T1. Can we compare this? We only know the relation T2 is greater than T1 and beta is greater than 1. How does that help? Can we comment on this statement? So since beta is greater than 1 is all we know, but we only have the comparison of T2 with T1. We don't know how this beta is going to impact. So if I so if it is T2 is greater than T1, that means 1 by T2 is less than 1 by T1, right? Now, if 1 by T2 is less than 1 by T1 and I have one factor being introduced, which is beta, okay, let's say I replace it by some other phi. So beta is equal to 1 by phi. So if I have phi over here and this phi lies in between 0 and 1, so does this relation still hold true? If it lies in between 0 and 1. So 1 by T2 is less than 1 by T1 for sure. And then we have another factor coming in, which is phi. And phi is going to phi, what would phi do? Phi lies in between 0 and 1. So 1 by T2 is already less than 1 by T1. Then phi, what would phi do? Phi would reduce 1 by T2 even more. So this should hold true, right? So the option is the lower frequency component, corner frequency of the lag component, which is 1 upon beta T2, which is this one, would be greater than the lower corner frequency of the lag component, of the lead component, which is not happening. We have a less than sign here and the question says greater. So this is definitely the wrong answer. Okay. Similarly, the higher corner frequency of the lag component, which is 1 upon T2, would be, we have to compare this to lower corner frequency of the lead component, which is 1 upon beta, lower frequency of the lead component, which is 1 upon T1. Okay, so we already know from here that T2 is greater than T1. So 1 by T2 would be less than 1 upon T1. But then it says it is greater. It should be smaller. So this is also incorrect here. Okay. Since we know that this is incorrect, I think the fourth option looks very similar except it is smaller over here. So this is definitely the correct answer because this is holding true. Similarly, you can check for the third option, the higher corner frequency of the lag component, this one, and the higher corner frequency of the lead component, which is this one. You have to compare both of these and you'll find it to be smaller. So this is also wrong option. So the correct option is D. I hope this is clear. If there is any confusion, then please tell me. Okay, I think it is clear. Let's move to the next question. Considering the magnitude plot of the Bode diagram of a typical lag lead compensator, we can conclude what? So how does it look like? How does lag lead compensator look like? It has 4 corner frequencies, right? So let's say we have 1 upon beta T2 over here, and then 1 upon T2 over here, 1 upon T1 over here, and gamma upon T1 over here. This would be the sequence, right? If it satisfies the T2 is it satisfies the same thing, T2 is greater than T1, so this would be the sequence, and this is how the corner frequencies would be located. So what would happen? The graph would look something like this. At first it would show lag, the benefits that we obtain from lag behavior, and later it would show the benefits that we obtain from lead behavior. So let's say this is 0 dB. It would start here. It would decay at minus 20 dB per decade. It would stay here. Then it would rise again because of lead, be here. So what is happening here? We are having a higher bandwidth because the lead compensator is there. At the same time, we are having low steady state error because the gain here is high. So this region, basically intermediate region, intermediate frequencies are attenuated. What are the other options? The high frequency components are attenuated. High frequency components in this region, they are not attenuated, so it is wrong. The low frequency components are attenuated. Here also it is not attenuated because we are having a high gain over here, so this is also wrong. Intermediate frequency band is attenuated is correct because this is attenuated, and the intermediate frequency band is amplified. No, it is not amplified because this has a very less gain, so we'll be able to attenuate this region. So the answer is an intermediate frequency band is attenuated. Okay, so we are done with today's questions. Any question up until now from these 15 questions? If there are, then we can take it. So we have one more session coming up on next Monday, which would be an extra session, and it would just deal with solving all the MATLAB questions. So whatever we have learned till now, starting from defining a transfer function, finding out where are the poles and zeros, step response, defining the stability of the system, routes, constructing routes array. When you are getting the step response of the system, then what are the performance specifications? How do we obtain them? Designing controllers, and then root locus, Bode plot, Nyquist plot, compensators, then all the performance specifications in frequency domain that we started with were gain margin, phase margin, etc. So so one question minimum related to all of these concepts will be covered in MATLAB. What I request is, please have MATLAB installed in your system. We'll start with very basics, introducing you to the command window, introducing you to the editor, to the workspace, where are the variables stored. We'll start with all of those very basic things, but then we'll go. So the agenda that I have for that day is, since all of the concepts are covered, now you know the theory behind it. MATLAB has commands or functions which directly take in the inputs from the user, and then you get the response. So for root locus, the command is just rlocus. So we don't have to do anything. We just have to write this, and we have to input the transfer function. That is all is required. For Bode plot, it is Bode. So these are very simple things, but apart from theory, we should be aware of all these things. So there will be a number of sample problems, around 10 or 12, and then we'll be constructing the plots for all of these. So my request is to please have MATLAB installed in your systems before you come to the next class. Apart from that, in case your institute does not provide you MATLAB license, we have another software called Octave, sorry, which is very similar to MATLAB in terms of syntax and the way it is programmed. So we can go with this. So in case you don't have MATLAB installed in your system, please install Octave and try to get some basics, that how do we define the matrices, how do we define an identity matrix. So if you're familiar with the basic syntax, it would be even better for you, because you'll be able to grasp all the concepts even more easily, as we'll discuss some of the things. And then yeah, so that will have next Monday. Next Monday is next Monday is 13th, MATLAB extra session on 13th 7/25. Apart from this, just to discuss what we have already done in the beginning, also when we were in the first class, I had told that please follow this book by Ogata. So this is a really nice book which covers all of the concepts that are covered in this lecture series. And then if you haven't still covered, you can please go and read this book. This is just the best book. Apart from this, you can also go for Norman Nice. From there you can read Control. So so here I've just put on what were the cases that we had for each week and how we have already covered all of them. So we started right from defining the dynamic systems to all the responses, defining transfer functions, the poles and zeros. Then we went to Bibo stability. We checked the effects of zeros, closed loop transfer function, performance specifications for second order underdamped system, right? We also looked at first order systems. We looked at the step response. We looked at various controllers, starting right from PID controller. We went into Rautharvis criteria, where we defined how do we check the stability of the system. If it is of higher order, if it is of order 0, 1, 2, 1, 2, we don't need to construct Raut's array. But as we move higher, we need to have a necessary and sufficient condition. So that was the reason. And then we moved to root locus and its application in control design. After this, we moved to frequency response, where we also after this frequency response, we saw that the magnitude may change, but the phase is shifted. It might be scale in magnitude and shifted in phase, but the frequency remains constant when sinusoidal input is provided. Then we constructed Bode plots, Nyquist plots. We also saw Nyquist stability criteria just yesterday. And then we dealt with relative stability, gain and phase margins, etc. Today we covered the lead lag and lead lag compensators. So all of these are covered. Then we have case studies coming up, which you will watch the lecture. We don't have explicit questions designed for case studies. So in the next in the next class, we'll be dealing with MATLAB problems only. If there is any doubt related to your assignments, related to any questions throughout the course, you may please bring it up there. It would be cleared. If there are no questions, we'll proceed with the MATLAB extra session. That is the plan. That is a 2-hour plan for the next session, which is supposed to happen on next Monday. So if there are any questions, please feel free to ask, and we'll meet on Monday at the same time. Thank you.